Whoa. Whoa. What was that?
That was dark matter, Dill.
That invisible stuff I tripped over? Really?
Yes, you blindsided dimwit.
Well, everyone's blind to dark matter, but what is dark matter? And is dark matter real? Let's see.
Now, where did this idea of dark matter come from? Well, dark matter is a hypothesized, non-periodic, weakly if at all interacting relic of post-inflationary cosmogenesis functioning as a gravitational
audience!
Audience? What audience?
No postdocs here, dumb it down, man.
Oh, I see them now. Unlike this dark matter here.
Dill, what are you pointing at?
Oh, you see, dark matter can't be seen or observed, so how do we know that it's a thing? Well, everything we see is composed of wavelengths, specifically wavelengths that fit here on a spectrum. Not a lot, right? Waves also tend to have some very interesting properties. They can bend and they can shift. And from our perspective, they can change color. Specifically, waves moving away from us look more red, and waves moving towards us look more blue. This is known as the Doppler effect. Now, this is crucial to understanding the velocities on the outer regions of our galaxies, because as we have used the Doppler shift effect, we have been able to record how fast these stars are moving on the outer regions, and they appear to be moving a little too fast. Using this discrepancy, though, Swiss astronomer Fritz Zwicky had an idea.
Dark matter.
That's right. Our best estimates and observations suggest that there simply is not enough normal matter for these stars to be gravitationally bound to the galaxy. Good job, Zwicky. Now, this is not where the story ends, of course. Dark matter would be continued to work on throughout many years and carefully observed. But how do we know this? And was Zwicky right? To determine if Zwicky was right is an issue. We can't observe dark matter directly because it's invisible. So we must look at what we cannot see.
That makes no sense.
Precisely. We have to observe its effects. We plot these effects as rotational curves. These rotational curves show the relationship between the star's radial velocity compared to its distance from the center of the galaxy. It makes perfect sense to me. The velocities of these outer stars doesn't match their predicted velocity. They're moving just a little bit too fast. With these measured velocities, a galaxy should not be able to hold whatever its shape is, and all of its contents would just simply drift away. Now, it's not just the galactic velocities that adding up, it was the mass. The physical mass of the galaxy was physically incapable of holding itself together. Galaxies then shouldn't be able to form, especially with stars moving at such high velocities. But dark matter is why they can. Dark matter, if considered to be a particle with mass, feeds the gravitational field established by other matter and keeps stars gravitationally bound to the center of the galaxy. This has been a consistent consideration among all the cosmological models and is the leading explanation as to why galaxies like ours can even exist. Now we have the reasons as to why dark matter needs to exist, but we haven't directly observed it, so this is not enough to prove it. That's when we turn to math.
Please keep this one simple, Dill.
Don't worry. The math confuses even our greatest physicists, so we'll limit our use of equations. To find an unknown mass in outer space, we can take the mass of a known object and find an unknown mass relative to that object. So we'll find the mass of the sun relative to Earth, and then we'll compare that to Saturn. The black hole's mass doesn't change, nor does its gravitational effect. This discrepancy, along with rotational curves and skewed velocities of stars, means that somewhere along the way, someone got something wrong.
The entire point is to prove we're right with dark matter.
I'm not finished yet. What about the Doppler shift? When matter decays, observable particles are released. Dark matter can decay as well and theoretically release particles that we can detect. In fact, particles of light or photons that are potential candidates for dark matter decay have a Doppler shift that can be calculated. Now remember, all of this is theoretical and that's why it's confusing. Let's also remember that there will be plenty more research to come. It's a very visible topic for something so invisible. Several missions are also already being planned out to more directly observe dark matter and prove of its existence.
We are quite aware that possibly no one really picked up on this, so ask your questions. We will try our best to answer.
Just like no one's actually picked up dark matter. Until me.